So our second presentation is on H1 thermal requirements. As clause H1 is compulsory for every build, understanding H1 requirements and planning for them through the design phase is vital. Marcel Herbke from Autex Industries, his presentation which will give us a general understanding of the thermal envelope and which products are specified to meet the H1 requirements. Marcel's presentation has been CPD approved for 5 points of the 30-minute presentation. And as I mentioned, we will be taking registrations at the end of the session. I'd also just like to mention that the presentations have been recorded, and we'll send out a link if you'd like to share this with colleagues. Now, Marcel is the National Sales Manager for Autex, managing 10 salespeople across the full insulation and acoustics range. And when Marcel's not at work, he enjoys playing football, soccer, and family time with his 2 children. So Marcel, welcome. Good to see you again.
Thanks, Matt. Good to be here.
And looking forward to your presentation. So over to you.
Brilliant. Thank you. Well, good afternoon, everyone. And yeah, as Matt said, my name is Marcel from Autex. Today we're going to talk about the H1 clause in the building code and specifically thermal design in buildings. So H1, it's been around since 1992 and in its current form since 2017, but it's amazing how many questions we regularly get about H1, and so I'm going to keep this relatively high level and sort of covering off the requirements for the majority of builds in New Zealand. But if you do have any specific questions about specific projects, then please do ask towards the end. So who are we? Who's Autex? Just a bit of background on Autex and why we're talking about thermal design. We're a family-owned New Zealand manufacturer, and we've been manufacturing here in New Zealand for over 50 years. And amongst other products, we make green stuff insulation, which is our range of thermal and acoustic insulation made from recycled PET. And as you can see there, some of you may be familiar with green stuff. It's a great product. As I said, it's made from recycled plastic bottles, and it's like a duvet, really. It's safe to touch, completely non-toxic, recycled and recyclable. It'll never slump. Comes in a range of densities and thicknesses, and it's great for meeting your H1 requirements. So, with that in mind, let's look at the exciting stuff, which is clause H1 of the New Zealand Building Code, which specifically stipulates that buildings must be built with an adequate degree of thermal efficiency and provide adequate thermal resistance to heat. Adequate in this instance being enough to conform with the relative standard, to comply with the relative standards. So we're looking at the minimum requirements really for the thermal envelope. And to give a bit of background, before 1978 New Zealand, there was no requirement for insulation in New Zealand. So if, like me, your home was built before 1978, chances are there is no insulation in the walls. There was a local government act that required a minimal level of insulation that came in 1978, but it wasn't, as I said earlier, until 1992 that the H1 clause was introduced. And there have been incremental changes since then in 2000, 2001. But I guess the biggest change came in 2007, and that was when double glazing was basically made mandatory. Now, there have been some small updates in 2009, an amendment in 2007, but we're now in 2020 and it hasn't really had a fundamental change for over 10 years. So potentially, particularly with MB talking about its program for climate change, there's potentially watch this space as far as an update of the H1 clause. It's interesting, as I say, the double glazing has basically been made mandatory since 2007, and we do still get a lot of questions about can single glazing be used in houses or buildings. So we'll cover that off as we go through today. So why is thermal design important? Well, as you can see through this, an uninsulated home, there's literally heat escaping everywhere through the walls and windows, through the roof. And it's fairly well documented these days as to the importance of a well-insulated home from an energy efficiency perspective. An insulated home is up to H1 standards, uses approximately 70% less energy to heat. And from a health perspective, there have been a couple of major major studies in New Zealand actually showing that every dollar spent on insulation results in a 2- to 3-fold return in health savings. Now, it depends on which study. One has a 2-fold return, one has a 3-fold return. Either way, I guess it's a fairly conclusive that it's doesn't only make the buildings more comfortable and better for society, but it makes economic sense as well. So that's the key thing to remember. Oh yes, okay. So this is actually passive housing. I guess the key thing to remember about the H1 clause is that it is a minimum standard. It is a minimum standard, and nothing is stopping. There is no maximum, so you don't have to build to it. You can build to it or above. So this is actually a photo of passive house that not only did the designer take a sort of special interest in the thermal envelope, but has also paid careful attention to other aspects such as ventilation, heat exchangers in the ventilation system, and building sort of over and above. They also put a pretty considerable amount of consideration into passive solar and thermal mass in this build. So, as I say, a point that I will continue to talk about through the presentation, H1 is the minimum standard, and there is no maximum. So, these days it's relatively easy to meet H1, and we'll look at exactly how. So before we go into the actual requirements, just wanted to look at a couple of definitions. Firstly, the thermal envelope. This is probably fairly self-explanatory and straightforward to most of you. This is all the elements: the roof, the walls, the windows, the floor that enclose a conditioned or inhabitable space. So from the external or the unconditioned spaces. So when a building, like a house, has an unconditioned space attached, like an internal garage, obviously the wall between the house and the internal garage is part of the thermal envelope. Or in a large build, maybe an office with a warehouse attached. As we'll get into the larger buildings, the warehouse doesn't actually have any insulation requirements. So the wall between the office and the warehouse would be part of the thermal envelope. The other key definition to understand is R value. So R, the R and R value literally stands for resistance. So the R value is a product's resistance to heat. So scientifically, this is actually a measure of energy, of what's passing through or needed to pass through a square meter of product to create 1 degree Celsius of change. But like I said, in layman's terms, a product's R value is its ability to resist heat, the transfer of heat. So the higher the R value, the better. And when we're talking about H1 refers to construction R value. So insulation has a product R value attached, but the H1 clause and all the standards actually refer to construction R value. And we'll look at what construction R value is, because every individual material actually has an R value, tested or not tested, as I say, which is its resistance to heat transferring through it. And if you think about components of a build, for example, a wall, it's made up of not just insulation, but your timber or steel framing, your plasterboard, your cavity potentially, and then your cladding. And so the construction R value is the R value of that element as a whole. Timber and steel, commonly used framing materials, have a lower R value than insulation, so they act as a thermal bridge, which means heat can escape through the framing. So for most standard construction types, the construction R value is lower than the insulation R value, and that is literally, as I said, because the thermal bridge that the framing provides. So what R values do you need? Well, that depends. The first thing to consider is actually the type of building. So you can see here in this diagram, there are really 3 possible outcomes. So if it's residential, it's easy. You have a look at follow the arrow for residential. The standard is NZS 4218. That's the standard regardless of the size of the build. And we'll look at that on the next slide, the requirements of 4218. If it's commercial, there are actually 2 choices. If there's less than or equal to 300 square meters of lettable space, then you also use 4218, which is the residential standard. If it's larger than 300 square meters of lettable space, then you use NZS 4243, which is actually a far easier standard to achieve. And I would suggest if there's going to be a review of the standards and H1, this is probably the area to target, because as you'll see in the next couple of slides, the requirements of 4243 are a lot less and a lot easier to achieve than 4218. And the third category for building type is actually industrial. And for an industrial build, there are no requirements at all. And what constitutes commercial versus industrial, we will look at in the next couple of slides. So these are the requirements under NZS 4218. So all residential builds and small commercial builds come under this standard. And as you can see, they've referred to R values there. As I mentioned earlier, those are construction R values rather than product R values. The other thing about these values that I've put up there, those are for non-solid walls. So, which are, again, they're the majority of walls in New Zealand builds, timber framed, steel framed, non-solid. If you are using solid timber, which to be honest, I haven't seen a lot of solid timber walls, or solid masonry walls, the standards are actually different, and we'll touch on that. The reason for that is a solid wall is thermal mass, and the thermal mass can contribute to actually providing heat in the building, giving off heat in the building. So as I mentioned, in 2007, that was the last significant change to the H1 clause. Pre-2007, the roof requirements were R1.9 in zones 1 and 2 and R2.5 in zones 3. So you can see quite a significant jump there. And the walls, it was 1.5 in zones 1 and 2 and 1.9 in zone 3, so not a massive jump. And the floor, there was no change to that in 2007, so it's R1.3. And to be honest, there is a clause in 4218 that actually states that a standard 100mm plus concrete slab on the ground is deemed to comply with this requirement of R1.3. So to be honest, to achieve 1.3 and the floor doesn't take is relatively straightforward and doesn't take much of a design consideration. However, if you're looking at a calculation, as we'll look at later, and you need to push more R value into the floor, it's very easy with perimeter insulation. But the big change, as I say, that did happen in 2007 was the glazing. Prior to 2007, there was no R value requirement for glazing in a home, hence the single glazing up and down the country in any house built before 2007. And then, okay, so if we just compare the two, so if you look at the requirements of a residential build or a small commercial versus the requirements of a large commercial building, you'll see, as I mentioned earlier, 4243 is a lot easier to achieve. In zone 1, all you need is 1.9 in the roof and 0.3 in the walls, and no requirement for floor glazing. Zone 2, a little bit of a jump in value in the walls and floor, but as I mentioned earlier, a simple slab on the ground will achieve that 1.3. And the same standard down in the South Island. So, yeah, I guess the key thing when specifying to think about is the size from a thermal design perspective is it going to be over 300 square meters of lettable area or below 300 square meters of lettable area? There's quite a difference in thermal design depending on which way the proposed building falls. And this is just a slide of a recent job in Sylvia Park, actually. And as I mentioned earlier, the H1 is a minimum requirement. This is 3.2 green stuff used in the ceiling there, so the design has gone over and above, which is something we would certainly encourage. And the final category, as I said, there are 3 categories: the small residential, small commercial, large commercial, and the final one is an industrial building. Now, there's no insulation requirements at all for an industrial building. What is an industrial building? Well, I've written it down here because the exact wording, any building or use where people use material and physical effort to extract or convert natural resources, produce goods or energy from natural resources, or repair goods or store goods from an industrial process. So that's why I've written those words: extract, produce, repair, or store. So essentially factories, warehouses, utilities, what have we got there? Power stations, aircraft hangars. So those, if it's an industrial building, then yeah, there's no requirement whatsoever, which I guess is fair enough. Right, so looking at 4218, what is an acceptable solution? So you're designing a house or a small commercial space, and you need to get H1 compliance. The first and the easiest way to get H1 compliance is the schedule method. The schedule method this can be used when the buildings have less than 30% glazing as a percentage of the overall wall area. And all the building elements use the same construction type. So it's the same type of walls the whole way around, the same type of roof for the entire roof space, and the same type of windows. Then all you have to do, it's a one-page document stating the total glazing area is less than 30% of the total wall area. Therefore, I'm using the schedule method. The construction R values of the various components are, and then you list the various components and the construction R values, and that's your compliance. However, less and less buildings these days have less than 30% glazing as a percentage of the total wall area. So the more common acceptable solution is the calculation method. Now, the calculation method comes into play when you have between 30% and 50% of the total wall area in glazing. So, well, as the name suggests, in this situation, you actually require a calculation. And the calculation, you calculate the overall heat loss from a reference building. The reference building is essentially the exact same building as the one you're designing, but has all the R values as per the tables I showed you below in each of the elements. That will give you overall heat loss. Then you compare that overall heat loss to the building you're building, and you may have less than R1.9 in your walls, but you can offset that by a higher R value in the ceiling. Or you may want to use some single glazing. I strongly would discourage that, but you may want to use some single glazing. You can offset the reduction in thermal performance there by a higher R value in the walls or in the ceiling. So so you do a calculation, and it basically gives you the average heat loss for the building, the overall heat loss for the building, which gives an average, and that overall heat loss needs to be less or equal to the reference building. So yeah, you literally need to work out the areas of each element and ensure that on average the building complies. It is a pretty blunt tool, because if you think, heat takes the path of least resistance. So if you're offsetting reductions somewhere else in the build and you're offsetting it somewhere else, the reality is the heat is still going to escape there. It is a blunt tool, but it's the best tool we have at the moment. Now, at Autex, we do H1 calculations for you under the calculation method. So if you do have any buildings that fall into that category between 30% and 50% glazing and you need an H1, send it through to us, and we can do your calculations for you and get you a pass. It is a relatively straightforward process, and we're finding most buildings tend to fall into this category. And the third category is the modelling method. The modelling method is required. You can use the modelling method. Well, two times you can use the modelling method. Actually, one is if you have greater than 50% glazing as a percentage of the wall area, and the other one is if you want to use thermal mass. If you've got some concrete maybe you're struggling to make it work using the calculation method, and so you want to use, you need to model the buildings. You need to look at the sum of the calculated annual heat load and cooling load of the proposed buildings does not exceed that of the reference buildings. Now, these models require an engineer with appropriate software. So if you do have more than 50% of your wall area in glazing, it is going to potentially cost you a little bit, and it's going to be slightly more difficult to get your H1 compliance. Right, so we're doing for time. We spoke earlier about construction R values versus product R values. the most common thermal bridges in a building element are the timber studs, dwangs or nogs, whatever you call them, wherever you're part of the country you're in, steel studs, the pathways that the heat can escape. So you can see here in this little table that I've put up the insulation. So we recommend a double layer or reducing thermal bridging as best as possible, because the heat does escape through the thermal bridge, as I say, the timber or the steel stud. You can see in this little table here, we've got the product R value and the corresponding construction R value down below. So you see if you put in an R2.9, you get a little bit of heat loss through the joists, so that becomes a 2.8. 3.2 becomes a 3, 3.4 becomes a 3.2. That's because of the heat loss through the thermal bridge, through the timber. So what we would always encourage as best practice is a double layer. So you put one layer in between and then one layer running perpendicular, running across the thermal bridge to reduce that thermal bridging. And as you can see, you get the true, you get a better construction R value simply by thinking about the specification and ensuring you're using your insulation the best way possible. You can see there's a 3.6 achieving a 3.3 versus a 3.5 actually achieving a 3.5 because you're reducing the thermal bridging. So that's really key, and it's the same with walls, and we'll get to that. This is an example. As you can see, I guess it's good, better, best. Good is on the far left. We've got the insulation sitting between the timber there. Better is on the right hand side where you're running it across the top, so there's the thermal bridging is reduced. Best would be putting it in between and above, so you're really reducing thermal bridging and increasing the R value, and that's what that detail would look like in practice, and that would be a very, very warm roof with a very high construction R value. Now, interestingly, the same goes for walls. And you may think, well, how can you reduce the thermal bridging in a wall because you need the timber in there for structure? 3604, the framing standard in New Zealand, doesn't actually the requirements for dwangs or nogs in 3604 are actually for a 45 by 45 mil dwang to sit in there. It doesn't have to be 90 by 45 mil, so you don't have to put a thermal bridge in the way we currently do. And I guess the frame and truss plants tend to pump them out like that, and the walls come pre-assembled, and it makes sense. But you'd be using less timber and achieving a higher construction R value if you were to use 45 by 45 mil dwangs, or you were to run your, if you've got the real estate, to run your nogs on the outside and actually significantly reduce the thermal bridging by having two separate layers running perpendicular. This example here was actually used in the passive house that I had a photo of earlier, and had an R value in the wall of 3.6. So it certainly can be done. And interestingly, with regards to 3604, the reasons for having 90 by 45 mil dwangs in our walls, it came from there is one reason that I can still see that is valuable, and that is your sheet lining. So your jib, you may want to pick up a join on the inside. But it was for keeping studs straight when we had wet timber, which with the kiln drying no longer really happens, or for fire, to stop the fire zooming up the walls, which now that you've got insulation in the walls, that doesn't happen anymore. For bracing, which now you've got your bracing, your jib and your cladding does the bracing. So yeah, there's no real requirement, and as such 3604 recognises that and specifies 45 by 45 mil dwangs as being acceptable. So this is actually a photo of my house in Beachhaven that I took a couple of weeks ago on a cold morning, and it gives the reason I've included it is it gives a really good example of thermal bridging. So the areas that you can see, those little kind of squares of condensation, are areas that I've recently relined, and obviously when I'm relining, I'm insulating. This was taken in the morning, and so the heat pump was running on 18 degrees or something overnight. The heat was escaping, well, across my entire wall, basically, apart from those little areas that are cold, and that's where the insulation is, and that's why condensation is formed on those areas, because it's cold, because no heat has escaped. But the great thing that this shot shows is how much heat is escaping through the timber. So there's absolutely no condensation forming on the timber. It's not cold. Heat is escaping through there. Those are little warm patches. And you can imagine, I mean, those are just quite graphic examples because that's where I've relined. But you can imagine if the entire wall was like that and you added up all the framing, it's a lot of heat loss across the wall. So that's a personal example of thermal bridging, and really shows the heat loss that does occur through the timber. So other considerations, glazing. I spoke about glazing, the change to the H1 clause in 2007. Ordinary single glazing has an R value of about 0.15. Standard aluminium double glazing has an R value of about 0.26. Timber frame double glazing has an R value of 0.31. But these days there's different levels, and like I say, heat will take the path of least resistance. Certainly looking at increasing the R value of your glazing, or even, I know it's not required under the building code, and it's not the designer's role as such, but curtains make a massive difference. So encouraging your clients to ensure these curtains or even curtain rails so curtains can be put up. And as I say, 4243, no consideration for double glazing. So that would be somewhere potentially where future amendments may focus. I did mention solid masonry design. Now the standard for solid masonry design is actually in the walls is actually R0.8, which is a lot lower than the R1.9 for non-solid timber frame, non-solid walls. Like I say, the reason for that is the thermal mass. If you're using solid masonry exterior walls and you want to apply R0.8 into your calculation method for that particular area, for the square meters of masonry wall that you have, you need to leave it exposed. If you strap and line it, you strap it, put your insulation in, line it, then then it is classified as a non-solid wall. So if you are going to use masonry and you leave it exposed, then you can put the reduced number in your H1 calculation for the area, the square meters of masonry wall that you have in your build. And if you're going to do that, best to position it somewhere where it does get some sun, so the thermal mass properties can really be utilised. SKILLION roof, this is about choosing the right product for the cavity. With a SKILLION roof, obviously you have a reduced cavity, but you still want to ensure you're going over and above the H1 recommendation. So yeah, selecting the correct insulation product for the cavity size to maximize the R value and ensure you've still got the airflow. Airflow is an important consideration. I'm not going to spend too much time on it because it's a category in itself. You can see cavi bats or castellated battens, but yeah, ensuring you've got the room in your cavity for the highest R value possible and sufficient insulation, and also you don't have room for a cavity in your walls necessarily. You have the cavity on the outside, just ensuring that you have your intelligent moisture management systems that if moisture's getting in, it's got a way of getting out. It's not a concern for green stuff insulation. Obviously it's polyester, it's not affected, but for the health of the wall, you do want to ensure that any moisture that gets in can get out. It's another design consideration. Recessed lighting these days not a major, but if you are renovating, you've still got old IC rated lights. Similar to a thermal bridge, you have to leave 100 mils clearance around, so that's just a hole that the insulation can go out. So if it's a renovation and you've got old lights, make sure you upgrade them to well, IC or ICF. CA is an absolute minimum. You can butt the insulation up to it, but the heat can still escape through the light fitting. So better off going IC or ICF, which means you can actually roll the insulation over the light fitting to reduce the thermal bridging. And the final point for large buildings, I probably should have spoken about this earlier. If you've got in the commercial space, quite a common design, offices attached to a warehouse. How do you treat these? You treat the offices separately. They're the only area that do need to have an H1. The warehouse space doesn't need it, falls under industrial. However, if you're doing rows of units and you've got some small office space with a warehouse, chances are the offices, if they're under 300, it's quite a high threshold for thermal performance. You may want to consider treating the whole unit as one, and as a commercial build, or as I say, breaking it out. And in that instance, you literally do need to treat the wall between the offices and the warehouse space. That's your thermal envelope. Like I said, that's a shot. That's our offices. That's our design office actually. And you can see in there that's a large space, and it's only designed to the standards in 4243. There's potentially I mean, we designed over and above, but a lot of commercial spaces around New Zealand. I'd certainly look at going over and above the requirements of 4243 if and when you get a chance. So in summary, key things to take away from this: the product R value versus construction R value, and looking at ways to reduce thermal bridging. NZS 4218 for any residential build and commercial under 300 square metres, 4243 for any commercial over 300 square metres of lettable area, and no requirement for an industrial build. Like I said, schedule method for less than 30% glazing. Major majority of builds, the category that falls into is the calculation method required, and here at Autex we can do those for you free of charge. As I've put there, H1 calculations, think about the glazing, think about reducing the thermal bridging, and think about downlights as a whole in your installation as well. And that is me.
Marcel, you mentioned that windows are usually the weakest part of the thermal envelope. There's different glazing options available. Can you elaborate on the difference of performances of those that we can choose from?
Yes. As I said, the minimum standard is 0.26, and that's just aluminium double glaze. But you can have low E, you can have argon filled, you can have thermally broken windows, you can have triple glazed windows, and the R values there can go anywhere up to sort of 0.4, 0.5, 0.6 apparently. So you can really look to double your thermal performance of the glazing by spending a wee bit more on the windows. Not probably what someone from an insulation perspective wants to be saying, but that's for the overall best performance of the building. That's a good place to start.
Yeah, lots and lots of options there, and obviously you can talk directly to the window and glazing companies to get the right solution there.